February, March 2018, paper 6, variant 2. Question 1. Student is determining the mass of a meter ruler. Okay, he's determining the mass of a meter ruler by a balancing method. He places the meter ruler on the pivot, places block Q with its center at the 95 centimeter mark. The student stated that it is difficult. Okay, it is difficult to place the mass accurately at the 95 centimeter mark. Explain how the student could overcome this. Okay, you can overcome this difficulty. Okay, it's quite easy to overcome this difficulty. One of the more popular solutions to overcome this difficulty is to simply take the average of the readings before and after the block. Okay, you have the mass. You can take the reading. You can take the average reading. For example, you can take the reading on this side. For example, it was 93, and on the other side, it was, let's say, 97. So we can find the average of these two readings. It's a very simple technique to make sure that the block is exactly at the 95 centimeter mark. Again, what should we say? He could take the average, okay, of the readings before, okay, and after the block. Okay. Can he move the block slowly until he balances it? Yes. Okay. Yes, he can move it slowly, but that's not actually the main problem with this question. Okay, the main problem now, the block is kind of balanced. It is balanced, but he's not sure that it is on the 95 centimeter mark, and that's the problem. He's not sure that it is on the 95 centimeter mark. And that's why he needs to make sure that how can he make sure he can measure the distance, for example, of the block and divide by 2 and make sure it's on the 95 centimeter mark. You have many different techniques. For me personally, I prefer this technique, which is quite easy to comprehend. Okay. Um, okay. You don't have to draw. No, you do not have to draw in this question. Okay, you may if you want to, but it's not a must. Okay. The student keeps block Q at the 95 centimeter mark and adjusts the position of the meter ruler on the pivot until the meter ruler is as near to being balanced as possible. Describe a method to find the point at which the meter ruler is as near as being balanced as possible. Okay. The question is, how can he make sure that it is balanced? Okay. How can he make sure that it is balanced? Very simply, he will move. Okay. In this question, okay, in this question, this is when we say, he should move the ruler, he should move the block slowly to the left and to the right. Okay, okay, he should move the block slowly to the left and right. In this question, we should say that until the block tips to either side, tips to either side. And the balance would be somewhere in the middle. Okay. The student now determines the distance A between the center of the block Q and the 50 centimeter mark. He repeats the experiment. He has some distances A and B. Now he needs to plot a graph. How can I plot a graph of A on the y-axis and B on the x-axis? Again, A on the y-axis and B on the x-axis. Okay, I need to scale the graph. Should be easy. You do not need to start your axes from the origin. Okay, A 25 up to 45. This would be a bit easy. Okay, 25, 30, 35. And then B started off 21.4 up to 39. So probably we will need to start from 20. Okay. 20, 25, 30, 35, and 40. Okay. This is a good scale. Let's zoom in and plot the points. 25 and 21.4. 21.4 or 21.5. Again, 21, 21.5, and 25. This is after three squares from 20. Hmm. You have a question? Hmm. 25.2 and 30.
مستر،
Hmm.
هو مش المفروض نعمل بلوتنج لكل البوينتس حتى لو عدينا يعني اللي هو أكبر رقم؟ يعني مثلا بعد 40 ممكن مثلا نعمل 45 ما نسيبهاش فاضية،
لا
ولا
لا
عادي؟
لا لا. Do not plot any. You don't have any extra points. You cannot plot points that are not there. Okay.
اوكي.
طيب. 30 35. 30 and 35. Okay, the points are quite easy in this question. 34.3, you can consider it to be 34.5 and 40. Okay, 34.5 and 40 should be here. Okay, and last 39 and 45. 39 and 45. Okay, the points are quite easy for this graph. Then we will need to draw a best fit line and find the gradient, G. How can I draw the best fit line? Best fit line again would be quite easy. Mhm. Straight line. Again, the line does not have to pass through all of the points. Okay, it doesn't have to pass through all of the points at all. This is a reasonable best fit line. What's your question?
بس لو احنا ليه مش كاتبين الزيرو؟
Zero.
اه.
Because he said you do not need to start from the origin. Okay.
هو لو ما قاليش كده اكتب الزيرو عادي يعني.
You do not need to start from the origin, preferably. يعني usually you do not يعني it would be better if you do not start from the origin, okay? Because if you start from the origin in this question, it would be actually wrong. Why? Because most of the graph would be empty. If you leave most of the graph empty, this would be wrong, okay? You have to fill up at least 70, 80% of the graph, okay?
ماشي.
Um, Again, finding the gradient, you have to use the triangle method. That's why I'm using the two furthest points apart. Okay, and I have to draw a triangle. I have to complete the triangle. And to measure the g, to measure the gradient, y2 over y2 minus y1 over x2 minus x1, 45 minus 25 over 39 minus 21.5. Okay, can someone calculate it for me quite quickly? Hmm. Over 39 minus 21.5. This would be 1.14. Okay, thank you. 1.14. Let me remove the line. Calculate the mass mr of the meter ruler using the equation mr equals m over, okay, uh, m over g minus 1, where m is 20 grams and okay, and we can use the g. Okay, yes, what's your question? 20 over 1.14 minus
هو
1.
should I keep the triangle ولا
Oh,
يعني
لا, you can, لا, leave you have to keep the triangle actually. Okay, in your
ليه؟
question, in your answer, okay, the line should be there. You should have the straight line, which is the line of best fit, and you have to have the triangle. Okay, if you do not draw the triangle, or if you remove the triangle, you might lose a mark. So just keep it as it is. Okay, 20 over 1.14 minus 1 would give me an answer of 143. Okay, 143. What is the unit I'm now calculating what? You have to know what are you calculating. I'm calculating the mass, okay, of the meter ruler. The mass would probably be in grams. If you use kilograms, that would definitely be wrong. Okay, 143 kilograms as the mass of 1 meter ruler, that's definitely not logical. So 143 grams is a logical mass for a meter ruler. Okay, yeah. Two students carry out the experiment correctly, but with different values for the mass of block Q. One student obtains values of B that are larger than those obtained by they are larger than those obtained by the other student. State and explain whether the larger values of B are likely to produce a more accurate value for the mass of the meter ruler. If I have a larger range of values, would that be more accurate or less accurate? Again, this is one of the very famous questions. This question is actually repeated a lot in paper 6. Is it better, okay, to have more values? Definitely yes. Okay, yes, it would definitely produce a more accurate value. Yes, it would produce a more accurate value. Why would it produce a more accurate value? Because it will decrease the percentage of error. Okay, more values, again, whenever we have more values always decrease the percentage, okay, the percentage of error. We cannot say they decrease the error alone, no, because the error is there, okay? No, you cannot say more accurate. You have to say why is it more accurate? Okay? Why is it more? Because the percentage of error decreases, okay? Because the percentage, why does the percentage of error decrease? Because they now have a less effect. The error is less affected when you divide it upon a larger range of values. Okay, that's why we always use at least 5 values for the range. Okay, if you use only 2 values, for example, that would be wrong. Okay. Okay. Question 2. We have 2 thermometers, thermometer A and beaker A, thermometer B and beaker B. Okay. In beaker A, we had 200 centimeters cubed of hot water. Okay. In beaker B, we had 100 centimeters cubed of hot water. Can we take the reading of each of these thermometers and record them in the table? Yes, we can do that. Thermometer A has a reading of 87. Okay, 87. Please, please do not write 80.7. I've seen this common mistake. It's not 80.7, it is 87. And thermometer B is 89. That's quite easy. 87 degrees and 89 degrees. The temperatures theta A and theta B, okay, at times 30, 60, 90. Can I complete the headings and the time column? Yes, I definitely can complete the headings and the time column. You have a question?
مستر هو لو عملنا من غير بوينت زيرو هننقص ولا لا؟
لا, it should be 0.0. I'm sorry. Yes, thank you for okay, for stating that. Yes, it has to be 0.0. 87.0 and 89.0. Thank you. The timings should be 30, 60, 90, 120, 150, and 180. The column headings, the time must be in seconds. It's not a must. It's not a must for the time to be in seconds, but because of the time in this question was in 30 seconds, 60, 90 seconds, so the column has to be in seconds. The temperature has to be in degrees Celsius. Okay, the initial temperature of the hot water in both cases. Okay, describe one precaution. I need one precaution which should be taken to ensure that the temperature readings in this experiment are as accurate as possible. Again, the thermometer, we have so many precautions for the thermometer. Okay, we have so many precautions for the thermometer. Again, you have to consider one of the precautions for the thermometer, not for the whole experiment. not for the whole experiment. I need one. I'm taking the temperature. So one of the precautions for the thermometer, for example, take the reading perpendicularly to avoid the parallax error. Okay, we can stir the water gently. Okay, stir the water gently. Okay, to make sure that you have an average reading. Okay, wait until the temperature stops rising on the thermometer. For example, you have so many, you have those main three precautions for any thermometer. Okay, write a conclusion. Okay, control room temperature. No, that's not one of the precautions that would be reasonable in this question. Again, you have to read the question. Just read the question very simply. Describe one precaution which would be taken to ensure that the temperature reading in the experiment is as accurate as possible. Controlling the room temperature would have been an answer to a question if I told you what is one of the controlled variables that you need in this experiment, for example. Okay, what is one variable that you have to keep constant for this experiment? Well, you could say the room temperature, you could say the initial temperature of the water, you could say the volume. Okay. Um, write a conclusion stating how the volume of water in the beaker affects the rate of cooling of the water. Justify. Justify, you have to write down, okay, numbers from the table. Okay, you have to reference the results. Beaker A started off at 87 and ended at 77.5, so we can find the difference. We can find the difference. 87 minus 77.5 would give a temperature difference of 9.5 degrees Celsius. 89 minus 74.5 would give a difference of 14.5 degrees Celsius. Again, correct me if I am wrong. There's quite a difference, okay? There's quite a huge difference between the two readings. So does the volume affect the rate of cooling? Yes, it does affect the rate of cooling. Initially, when I had a volume of 200 centimeters cubed, I had a rate of cooling of 9.5. When I had a volume of 100, the rate of cooling was only 14.5. So whenever the volume increases, the rate of cooling decreases. Okay. Um, 2B, yes, you can take the readings perpendicularly. Okay. As for C, you can write down, we have to write down as the volume. Okay. As the volume increases, okay, the rate of cooling decreases. This is worth 1 mark. The second mark, okay, the second mark is that you have to justify. You need to justify your answers, okay, by writing down some numbers from the table. Okay, when the volume was 200 so 200 centimeters cubed, okay, the temperature difference, okay, the temperature difference was equal to 9.5 degrees Celsius. When the volume was 100, okay, not 1,000, just 100 centimeters cubed, the temperature difference was 14.5 degrees Celsius. Okay. Now I need to calculate the rate of cooling, theta 0 minus theta 90 over T for which beaker? For the 100 centimeter cubed beaker, theta 0 minus theta 90. Okay, we will not take the whole range, only, okay, 100 degrees Celsius from theta 0 all the way to theta 90. 89 minus, okay, 89 minus 80.5 over T, which is 90. 89 minus 80.5 over T, which is 90 seconds. Can someone calculate it? Yeah. 5 divided by 90, 0.0945. 4. Include the unit. You must include the unit. Degrees Celsius, and this is seconds, so it has to be degrees Celsius per second. Degrees Celsius per second. Using the results for the 100 centimeter cubed. Again, for the same beaker, we need to calculate the difference or the rate of cooling in the second 90 seconds. 90 to 180, that would be 80.5 minus 74.5. Okay, 80.5 minus 74.5 over T, which is 90 degrees. Again, okay, 0.067. 0.67 degrees Celsius per second. Quite easy. The student suggests that it is important that the experiments with the two volumes of water should have the same starting temperatures. Okay, they have to have the same starting temperatures. Okay, all we did was we calculated theta 0 minus theta 90 over 90. Again, this one was theta 90 minus theta 180 over 90. Again, and see, you're too late. يلا. Okay, again, a student suggests that it is important that they have the same starting temperatures. State whether your values for x1 and x2 support this suggestion. Are they, does this support this? Do they have to have the same starting temperatures? Quite obviously, yes. Why? Why is it quite obvious that they have to have the same starting temperatures? In I, okay, the starting temperature was 89. In double I, the starting temperature was 80.5. That's quite a difference. And then when we calculated the rate of cooling over a time span of 90 seconds, the X1 had a rate of cooling of 0.094. X2 had a rate of cooling of 0.067. Okay, so there is quite a difference. Okay, there is a difference in the results of X1 and X2. Again, statement. Is it okay? Do we have to? Yes. Okay. Yes. Yeah. Okay. Yes. Agree. Okay. You have to agree. It's very obvious that you need to agree for this question. What does it have to do with the results? Again, x1 and x2. Are they? That's the question. Are x1 and x2 the same result? Okay. Are x1 and x2 the same result? No. x1 and x2 are different. Okay. They are very different. Okay, what does this have to do with the results, x1 and x2? If, for example, x1 and x2, they both had the same starting temperature, okay, this one was 89 and the other one was also 89, or this was 89.5 and the other one was 89, okay, they would have the same starting temperatures and they would have had the same rate of cooling, okay? Again, someone saying, are they within the limits of experimental error? Well, you can calculate them. You can calculate the limits. It's 0.094 divided by 0.067. You can calculate if you want to. 0.094 divided by 0.067. You can just divide it now. It would give you a difference of at least 40%. Okay? At least 40%. That's a huge difference. It is a 1.4 something. So this is a huge difference. So this is definitely not within the limits of experimental accuracy. That's why I'm saying, okay, you have to just calculate it. Okay. They don't have the same starting temperatures, so they do not support. Okay. Uh, Again, is it important that the experiments with the two volumes should they have, okay? They should have the same starting temperatures. Yes, they should have the same starting temperatures. Yes, I do agree. Okay. Yes, they should. Okay. Have the same, okay, starting temperature. Why should they have the same starting temperatures? Because, okay, X1, okay, starting temperature okay, starting temperature, okay, T1, okay, you can just write it down as the starting temperature of X1 was 89, and X1 was, and X1 equals, X1 was equal to 0.094. Okay, starting temperature of X2 was 80.5, and X2 was 0.067. The numbers are very far apart, okay? Numbers, okay, the numbers are far apart. Okay, the numbers 0.094 and 0.067, they are far apart. They are exceeding the limits of experimental errors. Okay, if they have the same temperatures or not. Yes, they do not have the same. Again, the question is asking me, is it important for X1 and X2 to have, okay, is it important for any experiment, okay? For example, if I'm using the same volume of water, 100 centimeters cubed, is it important for the temperatures, the initial temperatures to be the same? Yes, yes, it is important for the temperatures to be the same. Why? Because if the temperatures were different, as such the case, as the case we have, okay, if the temperatures are different as we have in this case, then the rate of cooling will be different, and that's the problem, okay? You have to have the same initial temperatures to have somewhat almost the same rate of cooling, okay? Okay. Another student plans to investigate whether whether more thermal energy is lost from the water surface, okay, from the water surface, or okay, from the sides of the beakers. Okay. Now they have a problem. They do not know whether most of the thermal energy is lost from the surface or if most of it is lost from the sides of the beaker. How could they test these hypotheses? How could they test these hypotheses? Very simply, all they need to do is what? They need to conduct two experiments. Okay? They need to conduct two experiments, okay, to test whether, okay, whether the surface of the water will lose more energy or the sides of the beaker will lose more energy. So what are the two experiments? One of the experiments is to simply add a lid. Okay. And the other experiment would be simply to add an insulation, okay, an insulator to the beaker, okay, wrap the beaker with an insulator. That's it. So one of the experiments, okay, experiment one, for example, okay, one experiment, okay, with an experiment with a lid and no insulation, and another experiment with a with insulation and no lid. And that's it. Okay. So you will test whether the surface will lose more energy or whether the sides of the beaker will lose more energy. That's it. Okay. What's your question?
مستر لما يجي يقول لي يعني you may draw لازم أرسم ولا لأ؟
لا, you may draw, you don't have to draw. Okay, you may. If you want to, you can draw. If you don't, it's okay. Yeah, moving on to the next question. We have a circuit X, we have lamps X and Y, draw a voltmeter connected so that it measures the potential difference across lamp X, That's it. Voltmeter across lamp X alone. Okay, you can draw it above or below lamp X. The student uses the meter to measure the current, record the current IS. The current would be, it's not 0.2 something. Okay, it's not 0.27. No, 27 would be wrong. Why? Because this is 0.3. Okay, this is 0.3. So 0.332 and 34. 0.34. Again, this is the current, I. So we have to include the unit. I would be A, amperes. Okay, the current would have a unit of amperes. A, 0.34 amperes. The student uses the voltmeter to measure the potential difference across X and Y, record the value of Vx and Vy. The Vx, well, it's quite simple, 1.2 volts. Vy, 1.9 volts. Okay, this is quite easy. She then measures the potential difference across both lamps in series. Okay, when they were in series, 1.4, what's 1.4? لا, you don't have, لا, this is not 1.4. The voltage of Vx is 1.2, not 1.4. Okay, it is 1.2. Why? Because every mark is worth 0.1 in this question. Okay, in the voltmeter, it's worth 0.1. In the ammeter, it was worth 0.2. Okay, doesn't matter. Okay, but in the voltmeter, it was worth, oh, it is worth 0.1. So 1.1, 1.2, and no, the voltage Vy would be 1.9. The voltage of Vs, okay, of Vx and Vy together would be 3.0 volts. Okay, 3.0 volts. Students should, okay, he's saying that Vs should be equal to Vx plus Vy. Is Vs equal to Vx plus Vy? What's Vx plus Vy? 1.2 plus 1.9. That is 3.1 volts. And Vs was 3 volts. Are they equal? Definitely yes. Okay, definitely yes. You can calculate it. 3.1 over 3. That would give a difference of only 3%. Okay. The statement, are they the same? Yes, they are the same. Yes, agree. Why? Because the numbers 3 and 3.1 are very close together. Are very close together and within the limits of experimental accuracy. The limits of experimental accuracy. That's it. Calculate the resistance, okay, R1 of lamp X. Can I calculate the resistance R1 of lamp X? Yes, Vx over Is. Vx was 1.2 over Is, which was 0.34. 1.2 over 0.34. This would give a resistance of 1.2 divided by 0.34. 3.5 or 3.53. Okay. 3.5 or 3.53. Okay, that's quite easy. The circuit components are to be rearranged. Lamps X and Y are in parallel. The ammeter measures the current in lamp X only. Okay, lamp X only. The voltmeter measures the potential difference across the lamps. Okay, this is quite easy. We have both lamps. They are now in parallel, but the ammeter is not measuring the total current. It's only measuring the current in lamp X. Okay. Yeah, we had the initial power supply and the switch. Power supply, and then the switch, lamp X, and the emitter with lamp X alone, and then lamp Y. Okay, this is X, and this is Y. And then the voltmeter to measure the voltage across both lamps. Okay. It's a very simple circuit. Any questions? Um, Horizontal. Oh, you can draw it horizontally. Okay, it's okay. Okay, yeah. Moving on to the next question. Voltmeter. Yes, the voltmeter is now measuring lamp X and lamp Y because it's parallel to both of them. Hmm. Soon sets up the circuit as described in EI. She measures the and records the current in lamp X and the potential difference in the lamps. She then calculates a new resistance R2 for lamp X, which is 8.3. The student notices that lamp X is very bright in this parallel circuit, but it was dim in the series circuit. Now it's very bright, but it was dim in the series circuit. Suggest how the temperature affects the resistance of a lamp. Justify your suggestion by reference to the value R1 and the value of R2. Okay. R1, what was R1? 3.53. R2 is 8.3. Okay. It's now 8.3. That's like 2 or 3 times, okay, the initial resistance. Now, lamp X is very bright. It is very bright at this instant. What does this have to do with the brightness? Or what does this have to do with the resistance? It's quite obvious. When the resistance increased, when the resistance increased, what happened to the brightness? It increased. Huh? Initially, the resistance was 3.5 ohms. Now the resistance has become 8.3 ohms. As the resistance increases, the brightness increases. That's it. They are directly proportional. Okay. Yep. As the resistance increases, okay, the brightness increases. Why? Because when the resistance was 3.1, 3.5, okay, it was dim. And when the resistance was 8, it was much brighter. Okay. Okay, 8.3 ohms has a higher brightness, or hmm, 3.5 was much lower, was much dimmer, was much dimmer because it was colder. Okay, has a higher brightness since it's hotter, for example, since the temperature increased, for example, the temperature, okay, increased. That's it. Okay, as the temperature increases, the resistance increases, and the okay, as the temperature increases, the resistance increases, and the brightness increases as well. Okay, good. Yeah, planning an experiment. Planning an experiment. A student is investigating the factors that affect the size of the crater, a hole that a ball makes when it is dropped into sand. You have a ball, you drop it into some sand, and he needs to measure the diameter of this crater. Plan experiment, which would enable you to investigate one factor. Okay, you need to investigate one factor. It's up to you. It is up to you to choose any factor that may affect the size of the crater. You have many factors that could affect the size of the crater. Again, you have some sand on the beach, for example. Okay, you have some sand. Okay, on the beach, you have some sand. But this experiment is conducted inside the lab, not in the beach. Okay, you're conducting this experiment inside the lab. You have a box of sand. Okay, and you have a ball, and you need to drop the ball and measure the height. Sorry, and measure the diameter of the crater. Okay, the diameter of the hole created in the sand. What is one factor that could affect the diameter You have many factors. For example, you have the mass of the ball. You have the height. Okay, you have the height of the ball. Okay. If you want to come up with other factors, okay, it could be okay, but these are mainly two main factors that would affect the crater, that would affect the size of the hole created. Okay. The ball size, again, the ball size probably would have to do with the mass of the ball. You can say the diameter. Again, you can say the diameter of the ball. It would be more accurate. Okay, because you can't measure the size of the ball. You can't measure the diameter of the ball. You can measure the mass of the ball, the material of the ball. Okay, that wouldn't be wrong. Okay, it wouldn't be wrong. Okay. Um, okay, let's choose, for example, the mass of the ball. Okay, let's choose the mass of the ball. This is the variable that I will be changing. This is the range of this is the independent variable in this experiment. What's the independent variable? What's the thing that I will be changing? The range of values. Okay, you have so many things you need to write down. Okay, which factor is being investigated? The key variables, any additional apparatuses. Okay, the method, the precautions. Okay, a suitable graph. Okay, I'll not be drawing a table, but I will draw a graph. Okay, what are the range of values? The range of values. What is the independent variable? What is the independent variable for this question? I will change the mass, okay, of the ball. What are some suitable masses that I can use? Preferably in the grams. Do not use 10 kilograms, 20 kilograms, 30 kilograms. That's not a logical, okay? These are not logical answers. We are conducting a experiment, okay, an experiment in the lab. You cannot pick up a ball which is 50 with 50 kilograms. Okay, that's illogical. Okay, I can use, let's say 50 grams, 100 grams, okay, 150 grams, 200 grams, and then 250 grams. Okay, these are some logical answers for the question. If you had used, for example, the height, okay, if you chosen that you want to change the height of the ball above the sand, again, you can use some values, which would be, again, in centimeters, for example, 20 centimeters, 40, 60, 80, 100 centimeters. Okay, you cannot use meters. You cannot go, let's say, 2 meters, 4 meters. You do not have 4 meters inside the lab. The maximum height would be 3 meters. That's it. Okay, so this is the range of values that I will be using, the mass of the ball. What are the key variables? What are the controlled variables for this experiment? Okay, the controlled variables. Controlled variables. I can say, for example, or you have to say in this case, the height of the ball above the sand. Okay, the height of the ball above the sand. The depth of the sand. Okay, okay, it's not wrong. Okay. The depth of I can write down depth of the sand. I can state, for example, the material of the ball. Okay, material of the ball. If you want to say the depth of the sand, it's okay. Okay. If you want to come up with any other controlled variables, they might be right. What are the apparatuses I will be using? Apparatuses. What are the apparatuses that I will be using in this question? I need I need two crucial apparatuses. One of them would definitely be the hmm, tape measure. You don't need a tape measure. You can actually just use a meter ruler. Okay, you can just use a meter ruler. Okay, uh, If you write down a tape measure, it wouldn't be wrong. To be honest, it wouldn't be wrong. So if you want to use a tape measure, okay, I'd prefer using a meter ruler. Okay, meter ruler, and definitely you need a balance. Okay, these are the two main um, apparatuses you need in this question. The meter ruler would be to measure the height above the sand and the diameter of the crater, and the balance would be to measure the mass of the ball. Okay, what are some precautions I could use for this experiment? Precautions. Okay, this is one of the questions, one of the very rare questions in which he asks you to actually state clearly some of the precautions you would need. Okay, take the reading perpendicular to the ruler. Okay, that is a really interesting precaution. Yes, we should take the reading perpendicular to the ruler. Okay. Um, okay. Take perpendicular. Take the reading perpendicularly. I don't know what's up today. Something's wrong with my writing. I'm sorry. Okay. Perpendicular to the ruler. Um, you can make sure, for example, that the measuring or that the balance is set to 0. Okay, set the balance. Okay, set the balance to 0 before taking the mass, for example. Um, what's the method I will be conducting? It's a very simple method. Okay, it's a very simple method for each mass of the balls. Okay, each mass. Okay, drop the ball from a okay certain height. If you want to state the height, it would be okay. For example, if you want to drop the ball from a height of 80 centimeters above the sand, okay, that would be okay. Drop the ball from a certain height above the sand. Measure the diameter of the crater in the sand. That's it. In the sand. Again, for the method, you have to repeat the same experiment for all of the stated masses. You must say that. Okay. Repeat the method for all the stated mm, masses. For this experiment, okay, for this question, he did not say that he needs a table. Usually, more than usually, actually, he says that he needs a table. For this question, he did not state that he needs a table. So we will draw actually a graph. Okay, he will draw a graph. The graph in this question would be quite easy. Why? It's quite logical. As the mass increases, the diameter of the crater would increase. Or, for example, if you had chosen that you will change the height, as the height increases, the diameter of the crater would also increase. Okay, so if you choose either of them, the graph would be almost the same. Okay, the graph would be the same. A suitable graph would be on the x-axis. I have to write down the mass of the ball, the mass in grams, and on the y-axis, the diameter of the crater, diameter of crater in centimeters. And this graph would be directly proportional. Why? Because again, it is a logical graph. As the mass increases, the diameter of the crater would increase. It would create a greater hole in the sand. Okay. Let's write down a quick conclusion. I know he did not state clearly that he needs a conclusion, but it would be logical to write down a very simple conclusion. And we all know the conclusion. We all know that it is quite systematic. Okay. What is a conclusion for this experiment? For each mass, repeat and take average. Repeat and take average. But for this question, we will not state, okay, we will not say record the readings in the table. We can say plot the readings, okay, on the graph. Plot the readings on the graph, okay. And instead of saying that we will compare the results, we actually already know the results. We already know that as the mass increases, the diameter of the crater would increase. As the mass increases, the diameter, okay, of the crater would increase. Okay? Okay.